Hello, welcome to this video. This is 6-7, and we are going to talk about definite integrals as an accumulator. And our learning intention is to use initial values with integration in order to calculate accumulation. Now, we have been talking and working with contextual problems and graphical problems in order to understand these connections between rates, amounts, definite integrals, and now accumulation. So just a couple of big ideas. On the AP exam, we're often given a graph or a rate function, and you're asked to find a total amount or a function value. Now, one thing that we're going to go ahead and start utilizing is this idea called accumulation. Okay, accumulation, and it is based on the fundamental theorem of calculus, what we have been talking about the past couple of days. Now, this also has another name that I'd like you to write down here as start plus accumulation, and really accumulation, I can't spell and talk at the same time. Really, the start is what I believe gives these problems away, and we'll see that here in a moment. So these problems occur in many different forms, and we've seen these. We've seen contextual problems, right, the story problems, particle motion, which I think really solidifies that concept of a position, velocity, acceleration, and graphs, equation. So these problems, they often gives a graph or a function that is a rate, and really what it gives is a derivative, and ask questions for the function value or a total value. Okay, and I think maybe what I'm supposed to put here is f prime. It'll ask about f prime of x and then ask for f of x for the function value. So, okay, what is this accumulation model, and what the heck am I even talking about? Well, I'm going to start off with the fundamental theorem of calculus, and that is that if I have the integral from a to b of f prime of x dx, which notice this is a rate, in order to find the integral of this, right, visually is the area underneath this curve, this is equal to the antiderivative of f prime of x evaluated from a to b, so f of b minus f of a. Okay, and really, like, think about this contextually. If I'm giving you a rate of how fast you're driving 60 miles per hour from time t equals 0 to time t equals 1, where t is in hours. After 1 hour, right, that's 60 miles times 1 minus 60 times 0, that's 60 minus 0. So you would have driven 60 miles, right? That's the total amount of miles. So here is the accumulation model, and just think about it like this. If I wanted to isolate f of b, if I wanted to isolate the final function value, I'm going to move this f of a over here, move it to the other side, plus f of a. Okay, let me get rid of that. And we end up with this model right here. So this is the accumulation model. The function value is equal to some function value a, generally comes before f of b, and we're going to then add the integral from a to b, right, from your starting value. And I'm going to go ahead and write start right here. This is where you start. And I'm going to integrate from a to the desired value, right, where you end at f of b, of that rate. And this will give you the final amount, the total amount, the net change amount. Okay, so the final amount is equal to the given amount, that's what you start with, your initial value, plus the integral of the rate. So let's go ahead and look at some of these examples. So we've been doing this with contextual or story problems, but we can also see it with just general functions here. Okay, so I have the function f prime of x, which is equal to sine squared of 3x minus 7. So if f of 5 is equal to 9, go ahead and find f of 8. Well, f of 8 is equal to, I'm going to use my start. So my starting value, how much that f of 5 is, that's 9. And then I need the value from 5 to 8 of my function, which is here, sine squared of 3x minus 7 dx. And so I'm just setting those up. I'm not going to actually integrate that value. We'll get to that coming up in the next couple of weeks, how we integrate that. But there it is. That's the start plus accumulation model. If I want f of 8, it's 9 plus the integral of the rate from 5 to 8. Pretty simple. What is f of 1? What is f of 1? Well, f of 1 is going to be equal to our initial value, which is f of 5. And notice my function value that I have, my starting value is further than f of 1. So I don't want to add an integral from 1 to 5. What I want to do is I want to take this away. So I'm going to take away the accumulation of the rate function, f prime of x, which again is sine squared of 3x minus 7 dx. Okay, and I'm taking that away from f of 5, my starting value. Okay, and lastly, for c, I'm just going to go ahead and set this up. F of negative 3. Okay, if I want this function value, I know what f of 5 is. I know that f of 5 is 9. And what I'm going to do is I'm going to subtract. I'm going to, again, subtract the area from negative 3 to 5. Of our function, sine squared of 3x minus 7 dx. Okay, and what we're going to go ahead and do now is we're going to utilize our calculators. I'm going to show you how to actually calculate this using your calculator. So go ahead, take out your calculators. And I'm going to go ahead and show you how we use our calculator in order to go ahead and calculate definite integrals. And that's very important. They have to be definite. They have to have limits. So I'm going to go ahead and I'm going to open up a new document. And I'm going to go to calculator. Now some of this will seem familiar. Notice I'm using that function f prime of x multiple times. I'm going to make my life easy and I'm going to go ahead and define. Again, you can go to menu, actions, define, or you can just type in define. And I'm going to define this function as f prime of x as what it is. So that would be sine. So trig. We have sine of 3x minus 7, I believe. And then I need to square this. So I'm going to go back to sine. Remember, be careful when you're working with trig. The calculator really wants you to square this whole sine function. They don't like the power of 2 right here. So I'm going to go ahead and add it after. Okay, so power of 2, I'm going to hit enter. And it doesn't like my f prime of x. I like to use the same variables just when I'm doing this. So that way, like when I'm writing stuff down, it's consistent with my calculator. But I can go ahead and I can call this you know, something else. So let's just call it, what if I just call it, I don't know. Let's say R, if it will let me do it. Yeah, R. Okay. And you could use a function here too. So here's R, and now I want to go ahead and I want to calculate one of these function values. So I'm going to start with f of 8 here. So f of 8 is 9 plus the integral from, 9 plus the integral from 5 to 8 of of my function here. So let's go ahead and do this. So menu, notice you're doing some calculus, okay? So, and I want integral. So there's your integral, okay? And before this integral, I have 9, so 9 plus, okay? And I'm going to integrate from, it was 5 to 8. 5 to 8. Okay, your function here in the first field is where you're going to place your function. I used R, so you could go ahead and type the function in, or if you've defined it, you can enter whatever, however you're defining it. Again, if you forgot, right here underneath VAR, your stored functions will be there. If you've already graphed it, you don't have to define it, it's already there. Okay, and then it's saying, hey, you're integrating with respect to what variable? X. So I'll hit enter. And there's the values. I don't want that. I want approximate, and I'm going to go to about 3 decimal places. So 10.432. There is our function values. So this is equal or approximately 10.432. Okay. F of 1. I want the same thing. Notice, right? But this time, f of 5, again, that's 9. I'm subtracting now the integral from 1 to 5 of my function here, sine squared of 3x minus 7 dx. Okay, so I'm going to go ahead, I'm going to enter this, and if you're doing a couple of these, one thing with your calculator, remember you can go up and highlight. So I'm going to go ahead and highlight this. So just use my tabs. Notice I'm tabbing up to it. It's highlighted. I'll hit enter. And then I'm going to edit whatever I want to edit. So I don't want to add the area. Remember, I want to subtract. And I am subtracting the area from 1 to 5. 1 to 5. So subtract that area. I'll approximate this. Oh, no. Approximate this value. And we get 7.058. 7.058. Okay, C. Notice that C is extremely similar, except now I want f of -3. So I'm going to subtract the area from -3 to 5. Okay, and that structure is extremely similar. So I'm going to go ahead and copy this, and then I'm just going to change that 1 to a -3. Okay. 5.022. 5.022. So this is equal to 5.022. Okay, and there you have it. Start, whatever starting value you're working with, plus the integral from the rest of the function. Okay, so here's example 2. This is extremely similar. I want you guys to go ahead and calculate these. I'll ask you to pause the video. I just want you to write the equation. So go ahead and please write the start plus accumulation model for each of these, and then I'll go ahead and show that. Then I'll ask you to pause and actually calculate those function values utilizing your calculadora. Okay, so go ahead and pause me, and then I'll show you what these as start plus accumulation models should look like. All right, here are the equations for the function values using the start plus accumulation model. So g of 4, I'm going to start with g of -3. I don't know if I included that -3, and then I'm going to add the accumulation of the rate function from -3 to 4. So the integral from -3 to 4 of g of x dx. Now make sure that your function here in your integrand is a lowercase g. That's very, very important. So here is g of x. Okay, B. Capital G of 0 is equal to capital G of -3. We're starting at G of -3, and then I'm going to add the area from -3 to 0, the integral from -3 to 0 of G of x dx. Now C is the one where we have to subtract that, the takeaway, because capital G of -7 is below my starting value, which is G of -3. So I'm going to subtract the area from -7 to -3 of G of x dx to get me back to G of -7. Okay, go ahead. Please pause the video. I would like you to calculate. and figure out these values, and then I'll show you the answers here problem by problem. So if you want to kind of unpause me in layers, you can go ahead and check this. All right, here is g of 4. So substituting for g of -3, we get 6 plus the integral from -3 to 4 of g of x dx, and this is 12.184. Now you should have defined, we're going to do this 3 times, so hopefully you defined a function within your calculator. You don't have to, but you're going to have to enter that function multiple times, or I guess just copy and paste it down. But I defined it as g of x, just so I have continuity with what I'm writing. If you define it as something else, like in this example we called it r, and you're going to write that on your paper, that integral, then you want to make sure that you write that define r on your paper so the reader knows that you're using that, okay? So anyway, here is the integral, and I approximated, and we got 12.184. Okay, so which I wrote here. Now, I want to talk about some of you guys who are going to use shortcuts and not even write any of this down. You have to write at least this top line down, g of -3 plus the integral from -3 of 4 of g of x dx. If you just put g of 4 equals 12.184, you're not going to get the point, because the reader needs to see that you're doing an integral to calculate this value, okay? So you're allowed to do it with a calculator, but they at least need to see this structure, okay? So this is very, very important. All right, pause me. I'll go ahead and I'll show you the answer now for g of 0. All right, here is the solution for g of 0. It is 6 plus the integral from -3 to 0 of g of x dx, which is equal to 2.773. If you put 2.772, that's fine. That's the truncated answer, and that would be accepted. Okay, and then here is c. Go ahead and calculate this. Here's the value for g of -7, which is -3.411. Okay, all right, so hopefully you did well there. Let's go ahead and look at a graphical example, which we know the AP exam loves to go ahead and give us. Okay, so example 3, given the graph of f prime, the derivative of f is shown above. Use the information to find the following. Given f of 0 equals 4, find f of 5 and f of 3. Okay, so again, they give us this starting value. They tell you what a function value is, and they ask for another function value. So find f of 5. Well, f of 5, I'm going to use my initial value, f of 0, whatever that is, and then I need to integrate the rate function. So f prime of x, I need to accumulate. What's that accumulation or net change from 0 to 5? So I know that f of 0, they tell us, is 4 plus the integral from 0 to 5 of f prime of x dx. I have that graphically, and that's just the area under the curve. And this is a triangle, so 1/2 the base, which is 5, times the height, which is 4, not 2, 4. Okay, and this is going to be equal to 4 plus 10, which gives us 14. Okay, so that is f5. I had what f of 0 was, and then I accumulated that net change from 0 to 5. Okay, next we have f of 3. So again, same structure. I'm going to take my initial value, and then I'm going to add the area from 0 to 3 of f prime of x dx. So we have 4 plus, now the area from 0 to 3, notice this is a trapezoid. So I'm going to have to take the average of the heights. My first height is 4 plus the height of my second function, which it's right here. We'll get to that in a moment, times the width, and we know that the width is 3. So this value here, notice it's slightly below 2, or slightly below, slightly below 2. But I want to figure out exactly what that is. Now this slope, I'm decreasing 4, right, from 0 to 5, I go down 4, and then my run is 5. So negative 4/5. Now I do that from 4, so I can go down every one, down 4/5, down 4/5, down 4/5, or I can kind of work in opposite direction. If I go this way, right, I know that this point right here, this height, that 4, that's going to be a positive 4/5, right? This is 0. I'm going down 4/5 every time. This right here is 8/5. Okay, so I'm going to add here at 3, 8/5. And I do want to go ahead and kind of clean this up. So 4 plus 1/2 times, I'm going to have, this is be fifths, so that's going to be 20 plus 8 over 5 times 3, so we get 4. I know you're like, come on, Jorber, just box it and get over with. Well, you know what? You don't know. This could be multiple choice, and probably is. Okay, so what do we get here? Okay, so 4 plus, I have 28 times 3, that's going to be 54. So 4, I'm going to say 40 over 10, right? That's 4 plus, we got 84 over 10. Okay, and this gives us 124 divided by 10, which is 12.4. Whew! Sometimes you got to flex those algebraic skills to make sure that you still got them. Okay, so I want you to go ahead and pause video. I want you to try the following problem part B and go ahead and then check back, see if you got it. Here is f of 0. F of 0, it is f of 5 minus the area from 0 to 5 of f prime of x dx. F of 5 is negative 1, and then you have to subtract that area. You're going backwards. I want to take away that area from 0 to 5, and that is 10, so we get negative 11. All right, f of 2. For f of 2, same idea. You got to start with f of 5, and you're going to take away the area from 2 to 5 of f prime of x dx. Now, f of 5 is negative 1, and then I'm going to subtract this area. This is, again, a trapezoid. I have 1/2 times, or actually not a trapezoid, it's just a triangle, but I do need the height at f of 2, which if I go up another 4/5, that's going to be 12/5. So that's our height times our width, which is 3. Okay, and you should have gotten this. Hopefully you simplified. This is going to be negative 10 over 10 minus, we have 36 over 10, which would give us negative 46 over 10, so a negative 4.6 would be your answer there. Okay? All right. Let's go ahead. Last example, I believe, yes, for this lesson, and this looks like a problem very, very common on the AP exam. So here we go. The graph of g of x is shown above for the values negative 5 to 12 inclusive and consists of 4 line segments and a semicircle. G of x, the antiderivative of g of x, is continuous on negative 5 to 12. So they're just telling you, hey, it's continuous. You don't have to worry about any discontinuities, and it just doesn't throw a wrench into our fundamental theorem of calculus. Okay, so A, given g of 2 equals 0, find g of 12 and g of negative 1. Again, here's your red flag, or not a red flag, it's just like a, hey, use start plus accumulation. G of 2 is equal to 0. So there's your initial value. Okay, so capital G of 12 is going to be equal to that initial value, capital G of 2, plus I'm going to go ahead and integrate from 2 to 12 of lowercase g of x dx, which is what we have, okay? So I know G of 2 is 0, plus now I have to calculate this area all the way from 2, which is here, to 12, man, which is all this, and then all of this. Okay, so one thing I like to do is I like to go ahead and just write what the area is right on the graph. So I know that this integral right here from this area from 2 to 6, that's a radius of 2. So a full circle would be pi r squared, so 4 pi, but I'm cutting that in half. So this is 2 pi, and because it's below the axis, it's negative. This area right here is 2, 1/2 base times the height. And then this area right here, you can see, if just by counting the rectangles here, that we have -8 in that area. Okay, so if we go ahead and kind of add all of that up, looks like we have -6 minus 2 pi, and we'll get our final answer, which is just -6 minus 2 pi. All right. And now g of -1, okay, is equal to capital G of 2 plus that area underneath g of x dx from -1 to 2. So we have 0 plus the area from -1, which is right here, all the way to 2. Okay, and that looks like a width of 3 and a height of -2. So that's going to be equal to -3. So plus -3, which just gives us -3. Right, that area 1/2 base is 3 times the height, -2. You get -3. Okay. Here is the next example, B, part B. Go ahead, please try to find these values, and I'll show you the answer here in a second. All right, here is g of -5. We use our initial value, g of -3, and we're going to subtract the area from -5 to -3. The area from -5 to -3 underneath g of x and the x-axis is a +2, so 5 minus 2 gives us 3. All right, and then the function value g of 4, if I use my initial value of g of -3, and I'm going to add the area under g of x from -3 to 4, that gives us 5 is our initial value, plus here I have -5, this value, -5, and then up until 4, that's 1/4 of 4 pi, which is just a pi, but it's below the x-axis, right? So this region is -pi. Okay, so you should have gotten 5 plus -5 minus pi, and that just gives us -pi. All right, hopefully in this video you learned about how to calculate function values using the accumulation model and given initial values. Please like and subscribe. I'll catch you guys in the next math video. See you next time.